I'm Anne-Margaret Crowe, one of the industrials analysts at Edison Group, and it's my pleasure today to be speaking with Dr. John Husnik, who's Chief Executive Officer, Chief Scientific Officer, and co-founder of privately held life sciences company, Renaissance BioScience. It's great to be talking to you today, John.
Well, it's a pleasure to be speaking with you as well, Anne.
Thank you. And my first question is this: why is the use of conventional broad spectrum pesticides so controversial at the moment?
They're so controversial due to the fact that they've had a positive impact on farming yields. However, long-term use has resulted in environmental problems. Firstly, mortality and toxic effects on pollinators, as well as larger animals that eat the pesticide-affected insects. And these compounds can transfer up the food chain. Secondly, not just direct, but toxins also accumulate in soil and water, affecting people living in the area directly. So thirdly, and most importantly, I think in a lot of ways, is health concerns for farmers. By breathing, touching during application, this is also an issue. And overall, there's a societal shift toward clean products and respect for the natural environment.
Thank you. And so if conventional broad spectrum pesticides are so bad for the environment, why don't legislators just ban pesticides altogether, stop farmers from using them?
I think as I just mentioned, pesticides are important as they help farmers grow more food on less land. It's estimated that without the use of pesticides, more than half of our crops would be lost to pests and diseases. Food crops compete with over 3,000 species of worms, 30,000 species of weeds, and 10,000 species of plant-eating insects. And if you take away an important tool from the farmer, you can see how this becomes a huge challenge. And I think instead of taking away a tool like this, it's probably just better to have a more effective alternative that is environmentally friendly. And this is something that we believe strongly in.
Okay, so tell us a little bit more about environmentally friendly pesticides, if this seems to be the way forward.
Thanks. I think one of the most interesting areas that we can actually look at is RNA. And RNA, as you know, is quite a hot topic now, unfortunately, due to the COVID pandemic. But mRNA vaccines have become something that people are much more familiar with nowadays. There's a twist to that a little bit. RNA is something that's very central to the dogma of biology, which is it comes from DNA, RNA, messenger RNA to protein. But there's another RNA part to it, and it's called RNAi. I for inhibition, for interference, if you will. And you can actually stop that flow of information. So using RNA, which is a nucleotide itself, which is very biodegradable, bio-friendly, but if you use it in such a manner that it can knock down an essential gene in an insect pest, you have something that's very specific according to the DNA of that insect itself. So you're not going to be harming, using a pesticide that's RNA based, you're not going to be harming those pollinators that we spoke of earlier or the animals. It's going to be very, very targeted. And that's something very powerful that these broad spectrum chemical pesticides are unable to do. So this is targeted, specific to the insect pest. And I think that's very powerful. And at the same time, being a natural component, a nucleotide, it is biodegradable. It would be, in the sense, so safe that the chemical pesticide that could kill 98 to 100% of some pest in the field, you and I could eat it and it would actually be nutritious.
Okay, that sounds a great step forward. And the company that you've co-founded, Renaissance BioScience, you're doing development in this area, aren't you? So could you tell us a little bit about that and what's particularly special about the technology that you're working on?
Yes, of course. So we took this a step further, understanding that RNA is very specific to what you want it to do. We thought, okay, how can we deliver that? One of the key problems, as you know, RNA is quite sensitive. It's quite fragile. It can fall apart in the environment very easily. Hence, you have to have refrigerators and everything else Double-stranded RNA, which RNAi relies upon, is more stable, but still it will be degraded in the environment probably too quickly to be applicable in an environmental setting. Through production, through other areas, and thrown into the environment, it's a little bit tricky. So what we have come up with is saying we understand yeast, baker's yeast, things that have brought us wonderful things such as wine, bread, beer, all these great foods that we love. It is a very safe organism. It's been part of humanity, is humanity's culture. It's one of the first organisms in biotechnology, if you will. So we can use this yeast as a delivery platform, but more importantly, it can also manufacture RNA. Yeast has this natural ability, it already has it there, to harbor naturally RNA inside of it. So we've cleaned up this RNA, if you will, other than what it requires for life. And we've been able to integrate into the genome some constructs that would then be specific to making this double-stranded RNA. So you would get then essentially a yeast that would be chock full of double-stranded RNA targeting a specific essential gene in a pest. For example, Colorado potato beetle, which we have already shown and done. What we do then is we inactivate the yeast. So you have this really protective shell. Yeast is wonderful because it has a cell wall around it. So it's really quite robust and stable in the environment. So once you have now a manufacturing unit, very, very effective in manufacturing because it's using to grow molasses, which is a waste product from the sugar refining industry. So you have this really cost-effective cell that's making enormous amounts of double-stranded RNA inside of it. We inactivate it, we kill it, and now it's this great delivery system. So we've dropped the price of manufacturing and delivery all in one unit. And this very stable product, as you will, can be applied onto the leaves, and it would provide, just as any other kind of pesticide, if you will, sprayed onto the leaves, mixed with water, all these kinds of things. And it could actually have, we believe, a little bit longer staying power than other RNA pesticides that are out there because of this protective shell. So potentially less applications, but very effective. So when the insect would ingest the yeast, the double-stranded RNA would be released in its gastrointestinal tract and cause that systemic effect that we're looking for. And we've shown this in our results to date. So we're quite excited about this very friendly, again, yeast being something humans and animals eat. It's in animal feed, it's in our food. So this would just be one little twist on a dead yeast that's carrying a lot of RNA, targeting a specific pest.
That's excellent, thank you. And I know we're focusing today on the crop protection product market, but can the technology that you're working on be used for other applications as well?
Oh, absolutely. So I think from a crop protection point of view, it's kind of the first area that we're entering, just due to the fact that we can really target a lot of insects. We have a huge area that we can go after with our entomology department. We also see a huge potential for animal feed, for applying in aquaculture, livestock animals, even companion animals. And what we have noticed to date, that because of this protective shell that I was telling you that this RNA is in, it's got incredible shelf life, high stability in industrial processes, so that we can incorporate this product as a prophylactic into feed. So when feed is being produced under high friction, high heat, for whatever it may be, for food, for shrimp, for animal feed, as I said, it can go into for poultry, swine, and other diseases that you can target inside the animals. It looks really, really interesting for us in that space as we grow out of crop protection into animal feed. And I think that's going to be something really important to reduce the amount of antibiotics, and as well as going after new diseases that are affecting animals that are more viral based. So we've done tests with white spot virus and shrimp, and you can literally just throw the feed, incorporating, which has our RNA inside of its yeast, also covered with feed, into the tank of water, and the shrimp will eat it, and we can actually do suppression of these viral loads on the shrimp itself. So you can go into all sorts of aquaculture, animal feed, and of course, we are animals ourselves, so we have a longer term view on how we can actually target certain cells, for example, macrophages in humans, for inflammatory diseases. So you can actually start knocking down inflammation inside of a human, and it would be more in a pill format, oral delivery, or other ways that are very much more flexible than, say, injection or some type of intravenous kind of solution. So this would be oral delivery because of that yeast cell for animals and animal feed, but also for humans. So the applications are broad, but we're starting off in crop protection because of the excellent results we have to date, targeting insects.
That's really fascinating. Thank you very much. Thank you very much for your time, and look forward to speaking with you again soon.